Black hole cosmology is the idea that our entire observable universe might be inside a black hole. This may sound like something out of science fiction, but it is gaining serious attention from some scientists. Most cosmologists support the Big Bang theory, but even some who are skeptical of black hole cosmology admit that it is plausible. Standard cosmology has described the origin and development of the universe through the Big Bang, cosmic inflation, and dark energy. However, deep theoretical challenges and new observational puzzles mean that it's worth looking for viable alternatives. There are a number of different proposals for how black hole cosmology might work, and I'll be looking at a few of them. So, here are 7 reasons for giving black hole cosmology some serious consideration. First is a similarity between the observable universe and a black hole. Einstein's general relativity is our best theory of gravity, and black holes emerge from that theory. Consider a vast ball of dust or gas. If that ball collapses, it should first become dense enough to form a star. If it collapsed further, then it could form a black hole. A black hole is defined by its Schwarzschild radius, within which mass is packed so densely that not even light can escape. This Schwarzschild radius defines the black hole's event horizon. If anything falls inside that event horizon, it can't get out again. Not even light can get out again. For any object, if you compress all its mass within this radius, you form a black hole. Now here's the interesting thing. If you take the total mass of our observable universe and calculate its Schwarzschild radius, that's very close to the size of the observable universe itself. What does this mean? Some researchers, including Raj Pathria in the 1970s, noticed this equivalence and theorized that the observable universe might actually be the inside of a black hole. This is not proof that we are living inside a black hole, but it's a provocative clue suggesting that our observable universe might be inside one. Reason 2 is another similarity, that there are extreme densities at the Big Bang and inside black holes. Einstein's theory of general relativity predicts something strange in the centre of a black hole. It predicts a singularity, a point with zero volume and infinite density. There's another place where a singularity is also predicted. The Big Bang theory is based on observations that distant galaxies all appear to be moving away from us. Trace that expansion backwards in time and, in theory, you would eventually go back to a singularity. General relativity tells us that space-time can be curved, like a ball for example. This curvature, when caused by a dense mass like the Sun, can mean that the light of distant stars can get bent as it travels towards us. So as the light from such a star passes close to the Sun, we see it in a different place compared to where it really is. An observation of this effect was the first confirmation of Einstein's theory. The idea of a singularity is that inside a black hole, space is curved in such an extreme way that all the mass of the black hole is pulled into a single point. Although singularities are based on Einstein's general relativity, many scientists are skeptical about whether they actually exist. For one thing, the idea of singularities assumes that nothing will prevent them from forming. But as mass gets denser and denser, we can anticipate that quantum mechanical effects are very likely to prevent a singularity from forming. Also, in other cases where a singularity shows up in theory, we don't find they actually exist in practice. Think of a drop of water just about to form below a tap. If you consider only the surface tension of the water, you can imagine that as a drop of water forms, it comes to a point, and that point would be like a kind of singularity. But in reality, water is made up of atoms and molecules, and so there isn't any actual point or singularity there. One variant of black hole cosmology offers a specific solution to the question of what was at the Big Bang, if not a singularity. According to an extension of Einstein's theory, developed by Élie Cartan and others, gravity may have a property called torsion, a kind of twist in space-time that becomes significant at extremely high densities. This torsion acts as a repulsive force, preventing matter from compressing into an infinite density singularity. Instead, there is a big bounce rather than a big bang. Whether this particular scenario is correct or not, the similarity between the intense gravitational density in both black holes and at the Big Bang are a second clue that black hole cosmology could be worth considering. Reason 3 is about consistency with the evidence. There are four main pillars of evidence for the Big Bang model, and black hole cosmology is consistent with these. Firstly, the expansion of the universe. This is based on the observation that distant galaxies are moving away from us. Their light is shifted towards the red end of the spectrum due to this expansion. Black hole cosmology models differ from the Big Bang only in that they explain this expansion as either due to an explosion inside a black hole or to a big bounce, rather than a Big Bang. The second pillar of evidence is the CMB, the cosmic microwave background. This was the first light that was able to shine across the universe after it cooled enough for that light not to be stopped by very active particles. Nowadays, due to redshift, that light reaches us at microwave frequencies rather than as visible light. As black hole cosmologies start with an event similar to a Big Bang, with a hot expanding mass eventually cooling as it expands, then they are also consistent with the cosmic microwave background in general. However, there are details in the CMB that any black hole cosmology theory will need to explain before it could be considered as a serious challenger to the Big Bang model. The third pillar of evidence is the abundance of light elements, such as hydrogen, in the universe. In the Big Bang theory, this is due to the light elements being formed during a short period when the initial mass is hot enough to produce hydrogen, helium and some lithium before it cools. This is also expected in general with black hole cosmology. The fourth pillar is how the large-scale structure of the universe forms and develops. Again, black hole cosmology predicts this happening in a similar way to the Big Bang model, but as with the light elements, more detailed predictions may be needed to challenge the Big Bang model successfully. In 2025, new evidence was discovered that has some cosmologists wondering whether it might tell us that we are inside a black hole. Recent analyses of some distant galaxies discovered that a significant majority, about 2/3, appear to rotate in the same direction, rather than the roughly even 50-50 split that is expected by the Big Bang model. Standard cosmology predicts that there should be no preferred direction of galaxy spin, so this evidence, if confirmed, raises the question of why there should be such a preferred direction for early galaxies' rotation. If our observable universe is inside a black hole, then, as all black holes we know are spin, we might expect such rotation to influence those galaxies inside it. Nikodem Poplawski and others have argued that black holes' intrinsic spin would be passed on to galaxies developing inside them, which could explain the observed preferred spin direction for early galaxies' rotation. This feature of early galaxy rotation preference was found in quite a small sample of galaxies, but if future surveys confirm this anomaly, that evidence could support black hole cosmology. Reason 4 is that black hole cosmology could provide an alternative to dark energy. Our observable universe is expanding, but that expansion seems to be accelerating. The reason for this speed up, according to the standard Big Bang model, is dark energy. However, although there's plenty of evidence for the accelerated expansion, there is no direct evidence for dark energy. One black hole cosmology model provides a different possible explanation for this speed up. Shockwave cosmology, proposed by Joel Smoller and Blake Temple, has the Big Bang as an explosion inside a black hole, producing an expanding volume of space and matter that includes the observable universe. Smoller and Temple integrate shockwaves into Einstein's general relativity. This produces a universe that looks essentially identical to the aftermath of the Big Bang, according to independent cosmologists. Along with Zeke Vogler, Smoller and Temple later proposed that this shockwave may have resulted in our part of the universe having a lower density than that surrounding it, thus causing the accelerated expansion that is normally attributed to dark energy. As their idea would mean that the acceleration is caused only by an effect of general relativity rather than mysterious dark energy, it's a simpler solution. And they also have a proposed test for this idea. Reason 5 is about the horizon and flatness problems. The horizon problem asks why the universe looks the same in all directions, even though distant regions, physicists think, should never have had the time to influence each other. The flatness problem asks why the universe's space-time geometry is very close to perfectly flat, which implies almost impossibly precise initial conditions at the Big Bang. Standard cosmology addresses these conundrums with a brief period of cosmic inflation, the idea that the universe underwent an ultra-rapid expansion, smoothing out differences and driving curvature towards flatness. However, inflation uses a hypothetical inflaton field and requires fine-tuned conditions to start and stop. Poplawski's black hole cosmology, with a torsion bounce, based on the torsion or twisting of spacetime which we discussed earlier, may provide an intrinsic solution with no need for an inflaton. Here's how. For the horizon problem, if the observable universe was born inside a black hole, then it started from a single causally connected region. When it bounces and expands, all its parts have already been in contact, naturally explaining the observed uniformity across vast cosmic distances. For the flatness problem, a repulsive spin-torsion interaction between the spin of tiny particles and twisted spacetime at enormous densities generates a rapid inflation-like expansion. This flattens the universe's spacetime. Moreover, this approach doesn't just mimic inflation, it does so with parameters fixed by well-established principles, spin and torsion, rather than unknown inflaton fields, and, according to Poplawski, it offers predictions compatible with observations of details in the cosmic microwave background of the CMB. Shockwave cosmology also resolves the flatness and horizon problems without the fine-tuning needed by inflation. However, both theories would need further development to rival the predictions of inflation theory before they could be seen as a better theory than the standard model. Reason 6 is about the entropy problem. Adam Frank, a physicist and astronomer, points out that the standard model of cosmology has a problem with entropy. He explains that entropy is a physicist's way of saying disorder. According to the second law of thermodynamics, any isolated system must evolve from states of low entropy to states of higher entropy. Disorder always increases. Considering the universe as an isolated system, this leads to the idea of heat death, that the universe will get more and more disordered and will end up in a cold and dark, high entropy state. But looking back in time, we can see that the entropy in the past must have been lower, especially so at the Big Bang. This is a puzzle. Why should the universe have been in such a low entropy state? Some physicists thought that inflation might solve this question, but as Frank points out, many critics argue that inflation models must be fine-tuned to give the right result. This makes an inflation-based solution look cooked up and arbitrary. How might black hole cosmology resolve this problem? If we are inside a black hole, that suggests our observable universe has formed within a larger parent universe. Smaller and Temple modelled our observable universe as part of an expanding volume starting from an explosion inside a black hole. As the density of matter in that volume decreased with time, due to continued expansion, the density would eventually fall below that needed to generate the black hole's event horizon. At that point in time, from the outside, it would seem as if a bright white hole suddenly appears. All the matter and stars that were inside the black hole suddenly become visible to the outside. However, this would not be like some abstract models of white holes which somehow supposedly continually spew out mass. Instead, this would simply be the reverse of the formation of a black hole. After becoming visible to the outside, the matter would continue to expand into that wider space or parent universe. That larger parent universe is likely to contain other similar expanding volumes produced by exploding or bouncing big black holes. We can consider a simplified view, just looking at two such volumes and how they expand over time. Zooming in to the place where they meet up, gradually they would form regions of denser and denser matter, where galaxies would collide and merge with one another. Matter would be coming into that region from many other expanding volumes too. Large black holes would form. More and more matter would accumulate in such regions of growing density. Eventually they would collapse to form hypermassive black holes, ones containing more mass than is in the entire observable universe. At a certain point, perhaps when they reach a critical mass, these may explode or bounce as new Big Bangs. The resolution of the Big Bang theory's entropy problem is this. The universe is no longer an isolated system heading towards a high entropy heat death. Instead, our observable universe is part of one expanding volume, which is destined to meet up with other expanding volumes, where gravity will then drive a collapse to form a hypermassive black hole with low entropy inside. From there, the whole process can start again. So here we have a kind of cyclic model with many Big Bangs spread out across space, with their matter eventually meeting up to form hypermassive black holes that explode as new Big Bangs. I call this the universe of opposites model. Reason 7 is about the perfect cosmological principle. The cosmological principle, which is a key part of the Big Bang standard model of cosmology, states that at the large scale the universe is homogeneous, that it is roughly the same all over. This happens at a scale much greater than that of individual galaxies. On such a scale, the universe is made up of a cosmic web of matter in which, on the largest observable scales, it's smoothed out and individual stars and galaxies are too small to see. The perfect cosmological principle is different from that. It says that the universe should be homogeneous in time as well as in space. We might ask, philosophically, why should the universe be homogeneous in space only, rather than both in space and time? The seventh reason for considering black hole cosmology is that in the universe of opposites model, it can conform to the perfect cosmological principle. The cosmological principle is used to support the Big Bang theory, usually with the claim that all the universe must be like the part that we can observe, homogeneous on the large scale. But we only see a very limited part of the whole universe, so that may not be true past our observable limit. The alternative version, the perfect cosmological principle, was proposed by Bondi, Gould and Hoyle to support their steady-state theory, which was once a rival to the Big Bang theory until evidence disproved it. At first, it might seem like black hole cosmology is not homogeneous at all if you only consider the universe to be a single black hole. But what if we consider a larger universe, filled with many expanding volumes, coming from exploding black holes, and also contracting volumes, forming new hypermassive black holes? If we then imagine this on a very, very large scale, both in space and in time, we could see this as a kind of enormous bubbling. In this scenario, all of the universe is constantly changing, but in a similar homogeneous way. So that was 7 reasons to consider black hole cosmology. To summarise them, first, there was a similarity between our observable universe and a black hole, that the mass of our observable universe would produce a black hole of a similar size to the observable universe. Second was a similarity in extreme densities between the dense concentration of mass at the Big Bang and that inside a black hole. Third is it's consistent with the evidence, in general, for the Big Bang, such as redshift and the CMB. However, black hole cosmology models would need to match or better Big Bang's detailed predictions to be a more serious challenger. 4 is a simpler alternative to dark energy. 5, that it might resolve the horizon and flatness problems without the need for a speculative inflaton field. 6, that it could resolve the entropy problem. And 7, it's consistent with the perfect cosmological principle. Is black hole cosmology ready to replace the Big Bang theory? No, not yet, but it's an intriguing idea with many reasons to consider it. Thanks for watching. What do you think? Tell me in the comments below, and if you like this video, please click the like button. Feel free to share it with someone you think might be interested, and click subscribe if you'd like to be notified about any future videos. If you'd like to read more about the Universe of Opposites model that I mentioned, search for WordPress Universe of Opposites, or click the link in the description below. Goodbye.